Hello, welcome to Two-Dimensional Harmonic Oscillators, Physics 360, Chapter 4, Section 4. So we're going to talk about this two-dimensional oscillator. So the force acting on this is equal to minus kr, where kr is a vector that has a component in 2 or 3 dimensions. In this case, 2 dimensions, but it could be 3. So you could add 1 dimension. So that's going to give us this system of equations. If we assume the mass is constant, then we can put in our definition for the net force equal to momentum, rate of change of momentum, and then plug in mv for momentum, and we get this, where we write v is the derivative of the position with respect to time. So we'll get one for the x-coordinate, we'll get one for the y-coordinate, and we could get one for the z-coordinate. Now, we've solved these already many times so far when we did harmonic oscillators. So our solution to this equation is this, where omega is the angular frequency or natural frequency of the system, a is the amplitude, and alpha is the phase angle. And then y, we get a similar equation, except we have a different amplitude and a different phase angle, and we could have the same natural frequency. In this case, we're only going to be talking about natural frequencies that are equivalent, so it's an isotropic oscillator. So we can find that frequency by taking the square root of k over m, and the idea is we want to describe the path of this mass as it moves in 2 dimensions. So we've got our equations, but they're equations of time. So what we want to do is remove the time component. So to do that, I'm going to rewrite the y1 this way, where delta here is a beta minus alpha, and if you plug that in there, you get the y thing. So I'm just rewriting this equation, adding and subtracting 1, basically, alpha in this case, and represent it this way. So then what I can do is I can treat this as the cosine of the sum of 2 angles. The angle I want is omega t plus alpha, and then this delta. So if we do that, we can express it this way. And I know what cosine over omega t plus alpha is. That is x divided by a. And then I can do a similar representation of cosine or sine here. That would be 1 minus cosine squared. So I can write it in this representation. So this is my sine term of sine of omega t plus alpha, and then here's my cosine term right there. And so I got the cosine of a delta and a sine of a delta. Well, we want to get rid of the square root. So to do that, I'm going to bring everything that's not in the square root on one side, and then we're going to square both sides, and then I'm going to group everything with x's together. So I'm going to bring it over to one side, and so I square this out. I get this expression. I get the cross term right here, and then I have this other term right here that has a sine squared. So if I rewrite that expression this way, bring the sine over, multiply sine, bring this over. Now I'm going to group the x squareds and a squareds together. So cosine squared delta plus sine squared delta is 1. So I can write it this way. And this is the expression we end up with. It's right here. And this should describe the path of any of these oscillators depending on what delta is. So what can we do with this? Well, let's choose. This is a abstract polynomial, both quadratic polynomial actually, and this is a very general quadratic polynomial. See right here, this little a would be 1 over big A squared, and this b here would be a minus 2 a divided b cosine times delta, so on and so forth. So if you solve this, you get particular looking geometric patterns that will show up. Either look like an ellipse, a parabola, or hyperbola, if this discriminant value here is a particular value. And so if it's less than 0, it's an ellipse. If it's equal to 0, it's a parabola. And if it's greater than 0, it's a hyperbola. So here's what we're going to do now. Is we're going to do some cases of what happens to this if delta has particular values. So if we take the difference in the two phases, because remember, delta is a difference in the phase angle for y and x, and so we say that value is 2 pi. What happens to our equation? Well, it drops right down to this. This is an equation for an ellipse. And then we can also look at pi. What happens if we make it pi? And if we make it pi, we get this expression. So how do we solve that? Well, the whole idea here is that we can rewrite that. This should be squared. So what I do is I have an expression squared is equal to 0. So then I can solve for y because either one of the roots is equal to, they're both roots equal to 0. So I solve for one, I get this expression. So y is equal to some constant times x. So this is going to graph out a straight line. This one would graph out an ellipse. And then if you looked at 0, when the phase difference is 0, you would get the same type of expression, except it's going to be positive. You go through all the same steps we did up here, except this term now is going to be negative, and you can solve for it. You would get a negative here. This would be squared. It's completely square. And what do these produce? Well, you get these trajectories that look like this, and this is referred to as an isotropic oscillator because the angular frequency of both oscillations are the same, and this produces this ellipse like this, and it's at a particular angle here. It's twisted. So you can see that is the semi-major axis, and that makes an angle with the x-axis right here, and we call that angle phi here. And if you solve for this using some geometry, you get this expression. So this angle is predicted by the values of our amplitudes A and B and the difference in the phase angle. In this case, our difference is 45 degrees. Our amplitudes are the same for both. We both go, it goes a maximum, and over here oscillates back and forth in the x direction, the maximum plus or minus 1. Same, and y oscillates back and forth here. The initial phase of alpha is 0, so that would make the initial phase of beta to be 45, so that we get the 45 value here. And this gives you an angle of phi as this with respect to this x-axis. So by looking at these graphs, you can determine some of the parameters of the oscillatory system, like amplitudes, how one period is related to another, or how one natural frequency is related to another, and that will allow you to relate to k's. So let's look at some more cases. Here's one where we got the straight line. Okay, so this is what I showed you earlier if the phase was either 0 or pi, and then here's a circular one. Right? Looks like an ellipse, but I think that's an Excel problem. It wasn't. The aspect ratio of these axes are not equivalent, so I didn't draw a circle, but you can see this is an amplitude of 1 here, this is an amplitude of 1 here, and it oscillates back and forth. It also, these are all the same frequency here, both oscillating the same frequency. So and these are the kind of things that are showing up. So you're going to be tasked with, if you know the initial conditions of the oscillator, that's how we find the phase angles and the amplitudes, as we know the initial conditions. of the oscillator, like what its initial velocity, what is its initial positions, so on and so forth, you should be able to draw one of these graphs based on the information that you know of these initial conditions and figuring out what the phase angles are and the amplitudes of these oscillators will be. So let's look at a non-isotropic oscillator. Well, what is a non-isotropic oscillator? Basically, the angular frequencies, if the oscillations in the x, y, or z axis are different, if they're different, it's a non-isotropic oscillator, and you get a graph that looks like this. Now, this is a special type of graph. It's called the Joyce figure, I believe. And this figure is closed because it comes back on itself over time. And so to have this, you got to have a special condition show up between the oscillators, frequencies, and the number of oscillations it takes to get back. Is that if the ratio of the angular frequency to n of each separate oscillator, if you can get these to equal, they're called commutative, and if they are, they produce these closed systems. Like this, you get these nice figures. If they're not, you don't get closed paths. It's going to take a very long time, maybe, to get it close back to its original position. And if you think about these linear oscillators, we approximate atoms in solids as oscillating back and forth under a simple harmonic motion. And this would give us a way of predicting the position of particular atoms in the solid as they oscillate back and forth, or predicting if they'll come back to original states or not. How this relates to our energy considerations? Well, we have potential energy in a three-dimensional oscillator, and the most general representation we can have here, you have one for the x, one for the y, and one for the z. And how can we guarantee this is an oscillator? We have different spring constants for each coordinate. Well, let's apply our definition of potential energies. The partial derivative of the negative partial derivative of the potential energy with respect to some position should equal to 4. And if we take that, there should be kx, not k. You get the spring constant in the x direction times the displacement in the x direction, and you get the negative sign, so that it's producing our force. So this is a valid potential energy function, at least in the x direction. You could do the same for x and y, and you get an answer. Well, it just so happens if the spring constants in all our directions are the same, you can write this potential energy with respect to r, and where r is the displacement from some origin, and the spring constants are all the same, and we're just going to call the spring constants constant. So you can write r as a vector, and then you can describe the energy in the system as being, you have kinetic and you have this potential energy. Well, that finishes up the end for two-dimensional or three-dimensional harmonic oscillators. We'll be doing a tutorial that allows you to go through all these things in class and get familiar with the type of figures that are produced and what initial conditions produce these type of figures. So I'll see you in class tomorrow.